It's time for fun with math, and today we're going to talk about what are called improper integrals. But first, I want to do a brief review of limits, especially if you notice limits as x goes to positive infinity or negative infinity. So real quick, let's just review these few problems. When you're working with limits as x goes to infinity, it's actually pretty simple to do. The idea is you think about what happens when you plug in a really big number, what happens to this expression. So I just plug in the symbol infinity and then try to interpret it. So here I plug in like infinity and I get 1 over infinity squared. And so I think to myself, like, what's 1 over a really big number squared? Well, it's like 0. And so that's the answer for this one. Over here, we plug in infinity again. I get e to the negative infinity. And so I need to interpret that. Remember, negative in the exponent means put it in the denominator, so this is actually 1 over e to the infinity. And e to the infinity, remember e is like 2.718, and you're raising it to a huge positive number, so you get a huge number on bottom and 1 on top, so again, it's like the number 0. Down here, we plug in infinity, and we have to interpret it, so you get ln of infinity, and so what's ln of infinity? Well, ln is a function that grows always. So, you know, it looks like this. It keeps going up and up and up. It grows really slowly, but it keeps going up, up, and up forever and ever. So that's my function ln of x. So it's clear that this should also be infinity. And so this function is going to blow up as x gets bigger. Now, the limit as x goes to infinity of tan inverse of x. So again, I'm going to plug in infinity and try to interpret what this means. So tan inverse of infinity. And so then I have to know a little bit about the tan inverse function. So to understand the tan inverse function, I have to understand the tan function. So remember what the tan function looks like. It has these vertical asymptotes right here at negative pi over 2 and pi over 2. That's where it basically blows up or blows down. And it looks kind of like x cubed in between there. So that's kind of how I remember the shape of the graph. So it looks kind of like x cubed. So there's a graph of tan of x. If you want a graph of the inverse, all you have to do is make the horizontal stuff the vertical stuff, and the vertical stuff the horizontal stuff. So it just kind of flip-flops everything. So I'm going to look down here at the graph of the inverse, and so instead of having vertical asymptotes, it has actually horizontal asymptotes. And you'll notice that the vertical asymptotes on tan of x are at negative pi over 2 and pi over 2, so the horizontal are at negative pi over 2 and pi over 2. And so remember, for the inverse, the outputs just become the inputs, and the inputs become the outputs over here. And so the graph basically looks the same, it just goes like this now. And so this is the graph of tan inverse of x. And so you can see as x gets bigger and bigger, it approaches this horizontal asymptote of pi over 2. So this is equal to pi over 2. If this was negative infinity, the answer would be negative pi over 2. Now let's look at this one, because this one, when you plug in infinity, negative infinity, you get an indeterminate form out. So when you plug in negative infinity here, you basically get negative infinity out, but it's absolute value. So you basically get like ln of infinity minus ln of infinity, which is this nice indeterminate form, infinity minus infinity. And so what that means, so let's write this down. This is an indeterminate form, which means you cannot determine this limit as given, so you have to do some more work. So oftentimes when you have this, you have to do some sort of algebra or use some sort of algebraic property. In this case, we're going to use a property of logarithms. So when you subtract logarithms, you divide on the inside. So we actually can rewrite this limit to find out what it is. So x goes to negative infinity of ln of, and when you subtract, you divide on the inside, so we have big absolute value. We have 2x minus 1 on top, and divided by x plus 1 on the bottom. Now when you take the limit as x goes to negative infinity, you basically get 2 negative infinity on top divided by negative infinity, so that's going to cancel, so you just basically have ln of absolute value of 2. Remember, when you're working with a rational expression and limits at infinity, here's my rational expression, all you care about are the biggest degree terms. So you have a 2x over an x, so it's really just a 2 as you go to negative infinity. Right, so in some sense, you can kind of cancel off these lower degree terms, because these are the only ones that matter as you go to negative infinity. So we get ln of 2 for this one out. All right, so that was just a brief review of limits, because today what we really want to focus on are what are called improper integrals. So what are improper integrals? So there's two types of improper integrals. There's one where you have infinite intervals. So that's like this example right here. You'll notice that infinity is in your interval right here that you're taking. And the second type of improper integral is sort of like discontinuous integrands, or if you want, they're unbounded. So that's this type of integral. And so what you want to notice in this one is that this denominator is 0 when x is equal to 1. So here the function actually blows up in between the limits of integration. So that's what we mean by a discontinuous or unbounded integrand. Right? The function is not continuous on this interval, basically, or at one of the endpoints. All right, so to work with these things, we should probably have some sort of idea of what we're actually doing. So let's just take a look at an example real quick. All right, so determine whether the interval is convergent or divergent. So what that means is sometimes this integral you're going to get out a number, and sometimes you won't get out a number. If you get out a number, it's considered convergent. If you can't get out a number, we'll say the integral is divergent. If it converges, we can find its value, and we're going to make sure we can use a calculator to draw a picture of the shaded region to check the work. So real quick, let's just draw a picture so you can see what we're actually doing. So we want to do this integral from 1 to infinity of 1 over x cubed dx. So what the heck is that? Right, what is it asking us to do? So what you can do is just draw a picture. So we'll just draw a picture of 1 over x cubed. So raised to the 3. We'll take our window to go from 1 to infinity. Now, we don't have an infinity button, so what infinity means is just a concept. So we just want to go to a really big number. So we're going to go to let's go to 100. And then we're going to zoom fit this. So zoom fit. So you can hit 0 if you want. I'm just going to scroll up so you can see what I'm doing. And so there's the function right there. It comes down and goes across. Now, this doesn't actually hit the x-axis down here. We're just zoomed out pretty far. So when I draw the picture, I'm going to draw it so I can kind of express what's kind of happening with the function. I don't want to draw exactly how my calculator's doing it. So it starts up here at 1, because when you plug in 1, you'll notice you get out 1. Right, 1 over 1 cubed is 1. And it just sort of comes down, and it gets closer and closer and closer to that x-axis right there. And so it goes on forever and ever and ever. And what we're trying to do, in essence, is try to compute the area underneath that curve, if it exists. It could be infinity, so it may diverge. But if it goes to a number, we'll say again, it converges, and it converges to that number. So in order to do this integral, we have to use our sort of definition that we've created. Now, way back when we made this definition, you probably have forgotten what it is, but if you have the integral from a to b of f of x dx, this is going to be equal to this sort of sum, I equals sort of 1 to n of these f of x sub i's times delta x's. So remember, this is sort of adding up all the areas of your rectangles. You can even, sometimes we put a little star here because x sub I is just a number inside one of our little intervals. And we take the limit as n goes to infinity. And that's actually our definition for our definite integral. If we want a little picture that goes with this so you can see what those symbols actually represent, we can kind of draw it here just for fun. So here's f of x, here's my a, and here's my b. And the idea is we're trying to figure out what this area is between a and b. And so in order to do that, we just split this interval up into nice little pieces. So remember, we have basically our x sub 0 right here, and then we have x sub 1, which is just a little bit over. It's that delta x over, and then you have x sub 2, and it keeps on going dot, 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 up until you get right here, which is your x sub n minus 1, and then b, of course, is your x sub n. So you split this up into nice little pieces, right? Just using delta x, you go over delta x each time, which is just the length of the interval divided up by the number of pieces you want in. And then what you do is that x sub I star right here, that's just a little point in the interval, right? So there's a little point right here, so that's like your x sub 1 star. There's a little point, wherever you want. You pick it wherever you want in that little interval right there. It doesn't actually matter where you pick it. X sub 2 star, and then anywhere you want in here, or wherever you like, you pick it wherever you like, x sub n star. And then you use that point to find the height of the function right above it. So that's f of x sub 1 star, and then you can make that little rectangle. And that's what this thing is representing, right? This is the height, and this is the length delta x, and gives you the area of that little rectangle. And then you add them all up, so you do the area of each of these. So this little height here was f of x sub 2 star. And you get that height, and you add them all up. You get the areas, and add them all up over here. You get the height up here. This is f of x sub n star. And when you add those all up, you get an approximation to the area. And if you let n go to infinity, that approximation will give you the area. And that's what this is asking for, the area underneath the curve f of x between a and b. So that was the definition of the definite integral. So we need to sort of extend that definition when we have this symbol infinity here. And it's actually pretty easy to do if you think about it. So what you're going to do is turn this improper integral into a definite integral. And the way we do that is we just smack a little limit down here. So limit as b goes to infinity. And we rewrite this integral as the integral from 1 to b of 1 over x cubed dx. So now b's not thought of as being infinity, it's just thought of being as some number. We don't know what the number is, but we can actually compute this integral and then run the limit on it. And that should give us the answer, if it exists. So let's see. We can compute this integral. This is equal to the limit. This is one of our types, so let's just rewrite it as one of our types, as b goes to infinity, of 1 to b, of x to the negative 3, so rewrite it as a power of x. And we can use that power rule for integrals, which just says you add 1 and you divide by it. So you have the limit as b goes to infinity. You have to keep that limit on there until you evaluate it. And so then we add 1 to negative 3, so we get negative 2, and then we divide by it. And so then down here we get negative 2, and we're going from 1 to b. And so then this is equal to, keep that limit on there to the very end basically, and I'm going to rewrite this as negative 1 over 2 b squared. Oh, I'm sorry, x squared. I'm getting a little ahead of myself here. So 2 x squared. And this goes from 1 to b. I'm going to evaluate the limit by plugging in my limits of integration, keeping that limit here. You can hit that at the very end. And so I'm going to get negative 1 over b, 2b squared. And then minus, a minus will be a plus, and I plug in 1, so 1/2. And then notice what happens when I plug in infinity for b. I have to interpret this, so this is going to equal negative 1 over 2 times infinity squared plus 1/2. And of course, this term here is going to be 0, because negative 1 over a huge number, which is, you can think like, you know, as numbers get bigger and bigger, it's closer and closer to 0, so the limit is 0, and so it's just equal to the number 1/2. So therefore, my integral I, let's call all the integrals I here. Therefore, my I converges. And it converges to 1/2. And you can even test it on your calculator. So just in case you think you may have made a mistake, we graphed that already. So if you take that graph, you hit second trace to put the calculate menu, go down to number 7, which is the integral, and just do, you start at 1 and you go to 100. We went to 100, just a big number. You can see that the number is like 1/2. It's not going to be exact because the limit's 1/2, so it's 0.4995006. So on here, if you want, we can write this is 0.4999, and there was then a 5006. So then a 5006, so 5006. So that's the number my calculator gave me. Now it's not the exact answer, but it's a great approximation and you can use it to kind of check your work. So that's what we mean by an improper integral. So to evaluate an improper integral, the first thing you have to do is you have to turn it into a proper integral basically, and then you slap a limit on in front of it to see what happens. And that's how we actually define what this thing is. Let's do another example where we have infinity as one of our limits of integration. So again, we're looking at the infinite interval type case. This one's negative infinity. So again, just so you can kind of see what's going on, we can graph this integrand. So on my calculator, just so you can see what's happening, so it feels a little bit more real, we can do 3 divided by, and then left parenthesis, and then we have 2x squared plus x minus 1, end parenthesis. And we'll make our window go from, now here we're going from negative infinity to negative 2. So I'm going to let this be negative 100, just a big negative number. And then it goes to negative 2. I'm going to go to zoom. I'm going to hit zoom fit. And again, when I graph this on my paper, I'm just going to use this here as sort of a sketch of what's sort of happening. So you kind of see that it kind of starts here and it's going to go up. So what I'm going to do when I graph it on here, I'm going to start down here, and then it's going to go, so start down here, and it's going to kind of go up to right here. And so I went from negative infinity, remember, to -2. And so if you plug -2 into it, you're going to get a height. If you want to see the height, you can actually use your calculator. It's really simple. You just press trace and -2, and it tells you the height at that point. So it's 0.6. So if you want to put a height on there, you can. So 0.6. And even before we start, we can determine whether we can see what the answer might be. So on my calculator, before I even evaluate this by hand, I can hit this and go down to number 7 and check out what the value might be here. So my lower limit, I'm going to use -100, which is a big negative number. And then I'm going to go up to -2. And so you'll see it'll shade in the region here eventually, and it'll pop out a number so you can kind of get a sense. So it's saying it's about 0.90125,286. So I'm going to copy this number down here. So what do I have? I have about 0.90. And what was that? So 125. Let's just do that. 125. And I'll just write ... It keeps going on. All right, so now that'll help me, check. So it looks like it's probably, and that's this area right here, right? So it looks like it's probably going to converge. If you don't get a number out, oftentimes your calculator will say error or something. We'll see an example of that in a little bit. And so that usually means it diverges. So I'm thinking it's going to converge. So this integral should converge. And now I want to find its value. So let's run the sort of definition if you want. So what's the definition? The problem is we got to get that -infinity out of its limits of integration. So what we'll say is that this is the limit, and instead of b, I'm going to use a now. And you may be curious as, why are you using a and not b? Well, it's actually because, the way that thing was defined, remember, it was the integral a to b of f of x dx. So different books do different things, but a good rule is, this is how it's defined, and we use a and b for limits of integration. So right now, my a is going to negative infinity. And so then we copy down my integral. And so I'm going to have the integral from a to -2, and then 3 over, and then I have 2x squared plus x minus 1 dx. All right, so now this is a definite integral. It's well defined in the sense that, we used that definition before. And so now I can evaluate this integral, and then I'll run a limit through it and see what happens. And so now this one, notice, we're going to have to use a technique of integration. It's not one of our types. So we have this sort of quadratic expression in the bottom, which I think I can factor. So I think this is going to be partial fractions. So let's come back here, and what I can do is I can factor that denominator here. But you got to keep that limit on there until the very end, which is kind of annoying, but it's got to stay there. So limit as a goes to -infinity. Of the integral from 0 to a to -2. And then the bottom, I think we can factor, so it's going to be 2x plus or minus something times x plus or minus something dx. And if something's going to come from the 1, so this has to be a 1 and a 1. And then we have to figure out how can we take a 2x and an x and turn it into a positive x. So I think this has to be plus, and that has to be minus. So there's a factorization. And then this is going to be partial fractions. And so the limit as a goes to -infinity of the integral of a to the -2. So this is good practice for us in using our sort of techniques of integration. So you'll have a, and then we'll have it divided by 2x minus 1 plus b divided by x plus 1, and then dx. And of course, now we need to go find a and b. And so the way that we do that is we take these two integrands, this one here, and this one here, and they should be exactly the same. And then when we clear denominators, here's what we get. So we'll get 3 equals, and we'll clear the denominators, so we'll get a times x plus 1 plus b times 2x plus 1. So I'm kind of skipping a step here, so I hope that's okay. Normally you would set circle here equal to rectangle, so this expression equal to that expression, and then clear the denominators. But once you do this enough, you can kind of skip a few steps and still be okay. It's like, oh, I clearly understand, what you're doing here. And then there you have two choices. You can equate the coefficients. That would be multiplying all this stuff out, and the x term, the coefficient on the x term should be 0, and the constant term should be 3. Or you could do this a lot quicker by simply plugging in numbers. So like if you want this one to be 0, you just let x be equal to -1. And what would that tell you? Well, you'd have 3 on the left. If you plug in -1, this term's going to go away, so it's just a great big 0. And then over here, you get b times, and if you plug in -1 on this one, oops, better be careful. I copied that down wrong. So right here, that's not a -1. That's not a positive one. That's a negative one. So that's important because that'll screw us up if we have the wrong sign there. Okay, so now it's right. And so if you plug in -1 there, that's going to be -2 minus 1, which is -3. And so this tells me that my b, when you divide both sides by -3, my b is going to be -1. So there's my b. And then to find my a, I'll let x equal 1/2. Because if you let x equal 1/2, this term's going to go away. 2 times 1/2 minus 1 is 0. And so this implies that 3 will equal, so I'm just letting x be 1/2, a times, and 1/2 plus 1 is 3/2. And so if you multiply both sides by 2, you get 6, and divide out by 3, you get back to 2. So this tells me a is equal to 2. And so now what I can do is I can come back here and plug in what I found, and then I can evaluate that limit. I can evaluate that integral and then evaluate the limit. So this is the limit as x goes to a, my bad, as a goes to, limit as a goes to -infinity. There we go. And we have the integral from a to -2, and we plug in here, so a is 2 divided by 2x minus 1 plus, and let's make that a minus then. So this one's a minus, because b is -1, so it'll be minus 1 over x plus 1, I want black marker here, dx. And so then when we evaluate this thing, remember how this works. This is the limit. You gotta keep that on there. A goes to -infinity. And then this is kind of a guess and check, if you like. So I would guess, it's ln of absolute value of 2x minus 1. If you want to put a 2 here, you can, but you'll see that when you take the derivative of this thing, you get 1 over the 2x minus 1. But don't forget the derivative of the inside. So the derivative of the inside is a 2. So you actually don't need that extra 2 in front, because where this 2 comes from is the derivative of the inside of this function. So we don't need that there. So there's my guess, and now it'll check out correctly. If you take a derivative of this, you'll get this back. And then minus ln of absolute value of x plus 1. You don't need to write plus c because we have a definite integral, so we're going from a to 2. And then this is equal to, now you could plug in your limits of integration at this point if you want to, but it's a little bit simpler if you use sort of the log laws. So the log laws say if you subtract logarithms, you divide on the inside. So I'm going to rewrite this as a single logarithm. It'll save me some work in the end. So absolute value of 2x minus 1 divided by x plus 1. And I'm going from a to 2. Now I plug in my limits of integration, so the limit as a goes to -infinity, and I get ln. Now if you plug in 2, let's see what happens. And I gotta be careful because it's not positive 2, that's -2. So there's lots of places for us to make mistakes. So that's a -2 right there. Alright, so if I plug in -2 on top, what do I get? I get -4 minus 1, which is a 5, which is really a -5. So I have a -5 on top. This is all absolute value 2. Then divided by, if you plug -2 into the bottom, it's -2 plus 1, which is a -1. And then that's minus what? Now I'm going to plug in my a. And so when you plug in a, you get ln of absolute value of 2a minus 1 divided by a plus 1. And so that's going to be equal, what's that going to be equal to? That's going to be equal to the limit as a goes to -infinity. And actually, I think we can evaluate the limit now. So let's just evaluate the limit. So let's evaluate this limit. So we're going to let a go to negative infinity. And what's going to happen? Well, right here, this isn't going to change at all. So you just get ln of 5, basically. So that's ln of 5. You can drop off the absolute value because 5 is positive. And then minus, when a is infinity, remember how you evaluate this limit, right? These little terms really don't matter here because a is going to basically infinity, right? Negative infinity. So it's really just minus ln of 2. It's just 2a over a, but the a's cancel, so you get 2. And that's because we're going to negative infinity. It only works for infinity stuff. And so that's going to equal what? Well, you can do ln of 5 minus ln of 2, or if you want to put them together, it'd be ln of 5 divided by 2. And that should be my answer. So let's check this to see if it actually works out like it's supposed to. So on my calculator, to check to see if my answer is right, what can I do? So on here, I got my answer 0.90125 blah blah blah, so I'll check this, ln of 5 divided by 2. Now remember, it may not be exact, but it should be kind of close. So I got 0.916. Now it's not as close as you might like, but the reason for that is you only went to negative 100, and negative infinity is a lot, quote, quote, bigger than negative 100, right? So, you know, if you took negative 1,000 here, you probably would get a better approximation. So this actually seems pretty good to me because, you know, this number you may not have gone far out enough. You may need to go to negative 1,000, negative 10,000 or something. So that's good. So therefore, my integral I, remember I'm going to call all integrals I here, so that's my I. Therefore, I converges. And it converges to ln of 5 halves. All right, so the last two examples we did, we had infinity as one of the limits of integration. What do we do if we have infinity as both of the limits of integration? So how do we work with problems like that? So from time to time, especially in sort of probability, you work with problems like this. Just so you can understand the idea, let's just look at the graph of this thing so you can see it. And so this is 1 divided by left parenthesis x squared plus 36 in parenthesis. And we're going to go from negative infinity to infinity. So on my window, I'm just going to go from negative 100 to 100. I just kind of take a big negative number and a big positive number. And so I'm going to hit zoom and zoom fit. So you can just hit 0, but I'm going to show you. I hit zoom fit. And you'll see that this function kind of goes up and then it comes down. And what's really nice about this one, it's the same on either side. So I'm going to draw this here. So I went from negative 100 to 100. And I saw that the function kind of does this. It goes up, and it turns around and comes down, and goes out here. And I can even find what happens at 0 if you really want to, because you can, hit trace and 0 real fast, and they'll tell you what happens when you plug in 0 to this function right here. And it says you get out, oh, it's not 1 over 36. Oh, that's not, so 0.0, that's not a nice number. So I'm looking back at the function. Oh, it's 0 is 1 over 36. So if you like, we can label that point. You don't have to do this. I just like to always find that, what is it doing right there. And what we really want to do is see if the area underneath this curve is finite or infinite in this case. And so you can even test it on your calculator. So let's see what your calculator says. If you hit second trace and go down to number 7, we can do the integral from negative 100 to 100 and hit enter. And it'll take a little bit, but it's going to spit out an answer here for us. So it says about 0.5036. So let's write that down because we'll want to look at that later. So it says this area is about 0.5036 ... And so that's the estimate it's sort of giving me. Now, so it seems like the integral probably will converge, but we're not positive yet. We're not sure yet. We need to actually, do the integral, evaluate the integral if we can. And so, how do we do one which has two limits of integration that are infinite? All right, so the idea is you're just going to split this integral up. Now, you can split it up wherever you like. The best point to probably split up is 0 because it's an easy point to work with. So if you have an improper integral that looks like this, what we do is we just split it up into two separate improper integrals. So like one that goes from negative infinity to 0, 1 over x squared plus 36 dx. And then we're going to add the integral from 0 to infinity of 1 over x squared plus 36 dx. So if you do each of these separately, and this one is a number, and this one is a number, then if you add them together, you get another number, and then we can conclude that this integral converges. Now this one's kind of nice. You can use some symmetry here. So notice that this function here is actually even. So remember the idea of an even function. The idea of an even function is the function is the same on either side. So f of x is equal to f of negative x. And you can see that in the graph here. This graph is basically the same as this graph on either side. And so what does that mean? Well, what that means is that you don't need to do both these integrals, because these integrals, this integral here, let's use a different color. This integral here and this integral here are actually exactly the same. And so what we can do instead is just turn this into one problem where we do 2 times the integral, and let's do the one from 0 to infinity of 1 over x squared plus 36 dx. And my reason for that is that the function here is even. And so you can just do one side and multiply it by 2, and you should get the same answer. So this will be equal to now, so 2 times the limit as b goes to infinity, because infinity is up here, of the integral from 0 to b of 1 over x squared plus 36 dx. And now how are we going to do this type of integral? Now there's actually 2 ways to do it. You can mess around with it algebraically, or you could turn it in, or you could do a trig substitution. Now I'm going to do a trig substitution this time, and then later on we'll talk about how you can mess around with it algebraically. But if you know how to mess around with this thing algebraically and see that it's actually a tan inverse of x, that's the antiderivative. Tan inverse of something, it's not just x, but tan inverse is sort of like the antiderivative. That's great. But I'm going to do a trig substitution on it, just sort of practice our trig substitution. And so for our trig substitution, I have to make a little triangle here. So let's make my little triangle. And so here's my triangle. Here's my theta. I have to make my sort of hypotenuse, so that's where this comes into play. So this is going to be the square root of that. So the square root of x squared plus 36. And then remember, this is like my a squared and b squared, right? There's my my square root of my, there's my c right there. So my a is going to be an x, and my b will be a 6. Right? So 36 is 6 squared. And so what I can do then is I can figure out what x is equal to. So x is equal to this side divided, I'm going to use this side divided by that side, so that's a tan of theta. So the tan of theta is equal to x divided by 6. And so my 6 times tan of theta is equal to my x. And I'm doing this because I have to make a substitution, right? So I have x, and that'll help me find dx. And so this is, the derivative of the left is 6 times secant squared theta, d theta. And the derivative of x is just 1 dx, so it's just a dx here. And so now I have my dx. I still need to find this thing right here, so that's this side. So what I'll do is I'll use this side and that's a cosine of theta. So a cosine of theta is equal to the adjacent over the hypotenuse. So that's the square root of x squared plus 36. I'll flip both sides to get this on top, and so if I flip the left, I get a secant theta. And if I, on the right, if I flip it, I just get this square root of x squared plus 36 on the top. And then that's divided by a 6 down here. And so then I have 6 secant theta is equal to my square root of x squared plus 36. And so what I can do now is I can plug back in. So over here, this is going to be equal to 2 times the limit as b goes to infinity of what? So I have this. Now I have to be careful. I can't write 0 to b because my limits of integration are going to change. Before I change them, I'm going to go over here and plug stuff in. So I have 1 divided by, and then x squared plus 36. Well, remember, that's just this thing down here squared. So I'm just going to square this, and that'll give me x squared plus 36. So if you square that, you get 36 secant squared theta times, and then here's my dx. Well, my dx is this thing here, so I'll take that, put that right here. So secant, or it's not secant, but 6, then secant squared theta d theta. And I got to change these limits of integration. So over here I have to think a little bit. So let's think a little bit. So what happens when x is equal to b? If x is equal to b here, because that's what x is, what happens over here? Well, this implies that tan of theta, just use this top thing right here, tan of theta is equal to what? it's equal to b over 6. And so to solve for theta, that's a 6 and that's a b. To solve for theta, I'll take tan inverse of both sides. So this will imply that theta is equal to a tan inverse of b over 6. B's and 6's look the same here, so I've got to be kind of careful. So b divided by 6. And so up here, I'll put tan inverse of b divided by 6. And then what happens if x is equal to 0? If x is equal to 0, because that's my lower limit of integration, that implies that tan of theta is equal to 0 over 6, which is 0, which implies theta is equal to tan inverse of 0. Now, tan inverse of 0, I know. It's sort of like what angle you take the tan of, you get 0 back, and that's equal to 0. And so the lower limit is still 0. And so what is this equal to now? So this is equal to 2 times. Keep a limit on there, so limit as b goes to infinity. And then the integral from 0 to tan inverse of b over 6. And then the secant squared business down here is going to delete that. It's going to cancel off that secant squared business up there. And then one of these 6's is going to cancel with one of those 6's. So I'm going to just basically get a 1/6 back d theta. So everything's going to cancel except for, 6 over 36. I can pull that outside. And so this is going to be 2 times 1/6, which is 1/3. And then you can take the integral of d theta. Remember, that's just theta. So I'm going to have a limit. Keep that limit on there. B goes to infinity. All the numbers can go out front. And the integral of d theta is just theta. And I'm going from 0 to tan inverse of b over 6. Then I just do what this says. And so this is 1/3 the limit as b goes to infinity. And so I plug in the upper limit and take off when you plug in the lower limit. So you plug in the upper limit for theta. So it's just tan inverse of b divided by 6. And then minus, when you plug in 0, you get back 0. So you're just doing this limit. And that's great, because now you're going to plug in infinity. And so what do you get? You get 1/3, and we'll interpret tan inverse of infinity over 6, which is just like infinity. And so we did this limit at the beginning when we were sort of reviewing some limit stuff. And we found that that was, this right here was pi over 2. And so this is going to be 1/3 times pi over 2. Which of course is equal to pi over 6. And so since it's a number, we know therefore my integral I is going to converge. So I converges. And it converges to pi over 6. And you can even check it. So we got that 0.5036. So let's check it to see what pi over 6 looks like. So second on, second quit, second pi divided by 6. And hopefully we get out like 0.5 something. And it's good. So that's 0.52. That's pretty close. It's not going to be exact because you only went out to negative 100 to 100. So maybe you did negative 1,000 to 1,000 to be a better approximation. Or negative 10,000 to 10,000. Even better than that one. Now what we haven't seen is an integral that actually diverges. So let's take a look at the next example. And in the next example, you'll notice it's a little bit different. The limits of integration don't have infinity in them because this is a sort of a different type of improper integral. So this is what we sort of say when the integrands are discontinuous. So when the integrand's discontinuous on your interval of integration. And what's really happening is it's unbounded. So you'll notice that this function, your integrand right here, this function right here is nice and neat, at 2, but when you try to plug in 1, the denominator is going to be 0, so it's sort of blowing up here. We can take a look at its picture, so let's just take a look at its picture right here. So y equals, let's clear this out. And so what we can do is we can plug this in, so x divided by, and then left parenthesis x minus 1, quantity squared. And we'll do our window going from 1 to 2. And then we'll hit zoom, and then we'll zoom fit it here. Sometimes it's dangerous when the integram, when the integram blows up, the function blows up. But let's see what happens. So we'll hit zoom fit, and there's the function. So it starts up here and goes down there. And so what's really happening is this is actually a vertical asymptote at 1. So over here, if you want, if we put a 1 here, and we're going out to 2, if you want, you can put a dotted line here, because that's what's kind of happening. There's a vertical asymptote for our integrand right there. And so it's sort of blowing up right there, and then it's coming down like this as we go out. And we're curious as to whether the area underneath this curve, all this area here, is finite or infinite, I guess, in a sense. So what's happening with this thing? Now, watch what happens on your calculator if you try to compute this. Your calculator can sometimes catch when these integrals don't converge. So we'll do this one, and we'll hit 1 and go to 2. And let's just kind of let it run here. And as it runs, it's going to keep going. It's trying to add up all this area, but it eventually gets to a point where it says, I can't do this. Something's kind of wrong here. And that's usually a good indication that this improper integral is going to diverge. It's usually a good indication that the integral is divergent. And so it's going to run. I'm going to let it run for a little while until until we get our answer, and I'm going to show you how we're going to do these types of integrals. So first thing you want to do is identify the problem. So remember, the problem is actually at this 1. Because when you plug in 1, this integram blows up, basically. You can see that from the graph. It's still running. So what we'll do is we'll take care of that 1 by rewriting this. There it is. Tolerance not met. Quit. Right? So it couldn't add up all the areas. It wasn't getting basically a finite number. It probably kept going up and up. So it's probably divergent when that happens. All right, so the way that we rewrite this is we're going to rewrite this as equal to the limit. And since the problem happens down here, remember the definitions, the integral from a to b of f of x dx. Since the problem happens at the lower limit of integration, we'll call this the limit as a goes to. And we're going to go to 1 now, but we're going to 1 from a side. So we're coming in from this side over here. So we're going to put a little plus up here. That means coming in from 1 from the right. And then write the integral a to 2. So it matters which side you approach 1. We didn't have to do that for infinity because basically there's only one way to approach it, infinity from the left, or negative infinity, there's only one way to approach it from the right. But we have to do it when we have problems with our integrants, when they blow up, basically, or blow down. And then so we're going to go from a to 2, and then we're just going to copy this down, x over x minus 1 quantity squared dx. And so now we want to evaluate this limit. Now, what's fun about this one is there's actually 2 ways to do this one too. So you could do partial fractions on it. That would be a good way to do it. But you can also do integration by parts. So just to practice integration by parts, we're going to do integration by parts because I already did a partial fraction problem. So this one's kind of fun because you can do integration by parts on it. So we're going to have a u here and a dv over here. And so our u is actually going to be equal to our x. And our dv is going to be this, I'm going to write this like this, so our x minus 1 to the negative 2 dx. Right? Remember, negative 2 means just 1 over x minus 1 quantity squared. So, this thing here, if you multiply these two things together, right? Multiply these two things together, of course, you get exactly this back. So they're exactly the same things. To find my v, that's a little hard to do, but you can actually guess and check on this one. So you just add 1 to the power and divide. And so this is just going to be equal to x minus 1 to the negative 1 divided by negative 1. And you can see if you take a derivative, the negative 1 comes down, cancel the negative on the bottom, becomes a negative 2. And derivative of the inside, of course, is 1. So that's what this is equal to. And we can rewrite this if you want as negative 1 over x minus 1, just so you can see when you do the sort of algebra, it's not so hard to do. And then du, of course, is nice and easy. Derivative of x is just 1, so you just get back dx. And so now we have to leave that limit on there until the very end, until we evaluate the limit. So it's kind of annoying, but again, you have to keep writing it each time. The limit as a goes to 1 from the right of, and then multiply down and minus the integral across. And so this is going to be what? So it'll be a negative x divided by x minus 1. So that's this times this. And then minus, but it'll actually be a plus because there's a minus there. So minus will be a plus. And then the integral, and I'm going to put the limits of integration here from a to 2. And the integral from a to 2 of this times this. So this will be a 1 over x minus 1 dx. And this integral is really easy to do. It's just an ln. So keep that limit on there. So limit as a goes to 1 from the right. And then what do we get here? So we get, just plug in the 2. We can do that. Plug in the limits of integration. So we get negative 2 over 1 minus, plug in the a. So minus and minus is a plus. And you get a divided by a minus 1. So I'm just plugging a in there. And then plus this integral, so I can find that antiderivative by guess and checking, so ln of x minus 1. And then that's going from a to 2. And so that's going to equal, what is that going to equal? So that's going to equal the limit as a goes to 1 from the right of negative 2 plus a divided by a minus 1, and then plus a what? Plus an ln of 1. When you plug in 2, you get 1 out, so ln of 1, minus a what? Minus an ln absolute value of a minus 1. And so let's clean this up just a little bit, because ln of 1 is equal to 0. And so what happens now is we get a limit as a goes to 1 from the right of negative 2 plus a divided by a minus 1 minus ln of a minus 1. And so now when we run a limit through this thing, let's see what's going to happen. So here, this one's not going to change. So you're basically going to get out negative 2. Plus, now what happens when you run a 1 from the right on this one? So think about this. This is going to be like the number 1. But on the bottom, what's going to happen is from the right, you're going to get some little number bigger than 1 here. So you have a positive number on the bottom, but it's going to be really close to 0. So let me keep the limit on there because it's hard to see. This is very subtle, but it's important that you see what's going on here. So let's leave it like this. And then minus, now this one, as you let a go to 1 from the right, this is just going to be a 0. All right, so this, and again, it's actually very subtle. Let's just leave the limit on. It's very subtle. All right, so I'm going to leave it on here so we can really look at what's happening. A minus 1. All right, so real fast, just so you see what's really occurring here, because this is very subtle when you're doing limits from a side. So this is going to be equal to, of course, that's negative 2. That's fine. But this thing here, so think about what's happening. Think about this function, a over a minus 1. So if you look at the function x over x minus 1, what happens is you have a vertical asymptote here at positive 1. And on the right-hand side, and you can graph this on your calculator if you want, on the right-hand side, it's going to look something kind of like this. And on the left-hand side, it's going to actually do something a little bit different. It's actually going to go down like this. So it matters which side you approach this. So if you approach this from the right-hand side, what's going to happen is this function is going to go up to infinity. So this limit here is plus infinity, because as you go to 1 from the right-hand side, you approach 1, this function continues to go up. And then it's going to be minus. Now here's where it gets a bit tricky. So you look at this function, ln of a minus 1. Right? So we'll look at the function of ln of x, absolute value ln of x minus 1, and see what happens. So what's happening here is at 1, you also have a vertical asymptote. And you can graph this on your calculator if you don't believe me. But that's what happens. You have a vertical asymptote at 1. And then this function, of course, is going down. It looks kind of like this. It's just ln of x shifted over. But it's going all the way down. So when you take this limit as you approach 1 from the right, so again, you're coming to 1 from the right, so you look, it goes all the way down. This is negative infinity. So it's minus a negative infinity. And these signs are important because what you have here then is negative 2 plus infinity, and minus is a plus, so you have plus 2 times infinity, which of course is equal to basically infinity. And so you can see that therefore this I, remember I'm calling all my integrals I here, so this I actually diverges. I diverges. It's very subtle, but that's why the notation is important, right? Mathematics at times is very, very, very subtle, so you have to understand the ideas very precisely. Okay, so there's an example of an integral, an improper integral that diverges. And my calculator actually told me that. So remember when you did the calculator here, and we tried to do this at the graph, when we tried to find that area, it gave me an error. And so oftentimes the calculator would do that if the improper integral does not converge. All right, so hopefully that makes a little bit of sense. We're going to do some more problems in class, but remember there are two types of integrals. One type has infinity as one of the limits of integration, so it would be positive infinity, negative infinity. Some of those integrals converge or diverge, and so we basically try to evaluate them to figure out which is which. The second type of integral, you don't have infinity in the limits of integration. What happens is you have a plus or minus infinity when you plug in one of the limits of integration or some number between those limits of integration. So basically, the idea is that the function itself is not continuous on that interval. When you guys get to class, we'll talk a little bit about what are called the comparison tests, because if you notice, it's kind of hard to run these integrals to actually evaluate them. So there's actually an indirect way we can often do this by using something called a comparison test and comparing them to some integrals that are kind of easy to decide whether they converge or diverge.